Hello. Can everyone see my shared screen here?
Yes, sir.
Oh, okay. Mm. All right. So before we begin, are there any questions regarding Buckets Elevators Module 4, the one I sent on, I think, Tuesday? Did you try any exercises on Buckets Elevators? Can you guys hear me?
Yes, sir, but your volume is very soft.
Volume is soft. I don't know what's going on. Can you hear me now?
Still very soft, sir.
Mm. Okay, how about now?
Yes, sir. That's much better.
Okay. Right. So let's quickly go over bucket elevators. Right. And then if you have any questions, we'll go over those questions before we move on to the next module. So after this, we are going to go through vehicle dynamics. Right. We're going to go through vehicle dynamics, show you how you would attempt problems based on vehicle dynamics. Right. Or the easiest way you can approach problems based on vehicle dynamics. And then tomorrow, uh, in our live session, we are going to go through what is this? Elevators. Elevators, I think I sent yesterday. So we're going to go through elevators, send in and all questions based on elevators. And then I'll also send you formulas which you can expect to use for flywheels. Flywheels is around 5%, which is like 5 marks in the exam. Right. Right. Now, regarding bucket elevators, right? You essentially have this diagram, right, where we have two pulleys, one being the tail pulley, right? So at the point of inlet, we have the tail pulley, right? And then at the delivery point or discharge point, we have the head pulley, right? So it's the head pulley that is connected with the motor, right? Now, we have, as far as the formulas that you can expect to use here, right? We have one where you have to calculate the speed, right? Speed of the chain or velocity of the chain, right? So that you use the square root of g times r times cos theta, right? Now the radius, right? The diameter of both the tail and head pulley tends to be the same. So the r, right, will always be whether you've been given the diameter of the tail pulley or head pulley, right? Because essentially they're the same diameters. So the R, whichever one you use, right, whichever R you use here, will be the same for either pulley, right? So the R essentially you will be given, right, because you'll be given either the diameter of the tail or diameter of the head pulley, right? And then this theta is the angle that the discharge point essentially makes, right? That angle normally you are given as well, right? Now from this, normally they ask you to calculate maybe the diameter of the head pulley, right? So from this formula, if you've been given the chain speed, you've been given the angle, then you can work out the R, right? And then from working out R, we know that we can get the diameter from the R by multiplying R by 2, right? So that's one of the formulas you can expect to use, right? And then we have this one, the length, right? That is the length of the chain, right? Length of the chain is essentially the length of the whole chain, right? Now, as you can see here, you have parts of the chain going around this pulley and part of the chain going around this pulley, the tail pulley, right? So essentially to get the length of the pulley, you do that by adding up the center distance between the two pulleys, right? So accounting for the length of the pulley from here to there, right? So essentially, it's two times the center because you are accounting for the length of the pulley this side and this side, right? So the length of the pulley will essentially be two times the center distance, right? Accounting for this side as well as this side, right? So from here, right, from this center, right, to that center. But because you're considering both sides, you then say two times the center, right? Plus, and then you account for the bit of the chain that goes around the two pulleys, right? Now, because the chain goes around, right, half the circumference of this pulley as well as half the circumference of this pulley, that essentially makes a diameter, right? A whole circumference, right? Meaning that you can essentially take that distance as essentially the circumference, and the circumference being equal to pi d. That is why, or that is where this formula for length comes from, right? So it's two times the center distance, right? And then plus the circumference, right? Where you are essentially accounting for the bit of the chain that goes around the two pulleys, right? So if it happens that some of these formulas are not in the formula sheet, this is one way you can remember them, right? By looking at them from the perspective of the diagram itself, right? Right, so that's the total length of the chain. That will be in meters. The diameter will be in meters, right? And then the center distance will also be in meters, right? And then we have this one, which is the number of buckets per second, right? That refers to the number of buckets that pass through the discharge point per second, right? So B per S is essentially the number of buckets that pass through the discharge point per second, right? So to get that, you simply use the speed of the chain, right? And you divide that by the spacing being the essentially the spacing or the distances between each of the buckets, right? So the spacing is essentially the same, right, throughout is the same throughout the throughout the length of the chain, right? Hence the spacing, you only have just one spacing because the spacing between the buckets is essentially the same, right? So that will also be in meters, right? And then you get, now regarding M, right? There is essentially two M's that we deal with. There's M dash and there's M dot, right? M dash we essentially use in belt drives, right? That is the mass of the belt per meter length of the belt, right? And then M dot is essentially the mass flow rate, right? So M dot refers to kg per second, hence us calling it the mass flow rate, right? Now to get the mass, I've given you two formulas to calculate the mass, right? One where you use the mass in tons, right? And one which you use if you've been given the mass being delivered in kilograms, right? So to get M dot, right, if instead of having to convert, you can simply just use either of these formulas depending on how your mass delivered has been given to you, right? So if your mass delivered has been given to you in tons, you can simply just use this, right? Substituting the mass being delivered in tons, right? And then whatever you get here will be in kilograms per second, right? Similarly with this one, right? If you've been given the mass being delivered in kgs, you then use this one, substituting the mass being delivered in kgs here, and whatever you get will be in kilograms per second. So both formulas will give you the mass flow rate m dot in kilograms per second, right? So if it's been given in tons, you simply substitute the mass being delivered in tons here exactly as it is, right? And then when you calculate, whatever you get here will be in kilograms per second. Similarly with this one, and if you've been given the mass delivered in kilograms, you use this one, substituting the mass delivered in kilograms, and whatever you get here will be in kilograms per second. So both formulas will give you the mass flow rate in kilograms per second, right? Now the shift hours, they will be given to you in hours, right? Right. This I've already explained. That's the mass of the material being delivered per second, mass flow rate, right? Or you can simply just call it mass flow rate, right? And then we have the mass of the material in each bucket, right? Essentially, with bucket elevators, right? We are essentially, or with bucket elevators, what we're essentially trying to do is to get whatever material, right, that is coming at inlet and having it delivered to the discharge point. Right, the material doesn't really matter; it can be any material, right? Now, sometimes they do require us to calculate the mass that is in the bucket or the mass in each bucket. Right, so to get the mass of the material being delivered in each bucket, you use this formula, right? So the mass in each bucket or mass per bucket is equal to the mass flow rate divided by the buckets per second, right? Of which these two formulas we've already gone through, right? Or the formulas to calculate both m dots and the buckets being the buckets essentially passing through the discharge point per second, we've already gone through, right? Now this here, mass of material in each bucket, right? You simply use this SI unit essentially. Right? So there will be, because you're looking at mass, this will be in kgs, right? And then kgs per bucket, right? So you can simply just use this as your SI unit, right? And then you have H, right? H is the vertical distance of the discharge point, right? Right. So H is the vertical what is this vertical distance of the discharge point, which will be in meters, right? Essentially, if you happen to forget, look at it from the perspective of the diagram, right? So the height essentially is the height from here, right, to essentially there, right? Hence, to calculate the height, you simply say it's the center distance right? Plus the radius plus this radius. Now, radius plus radius, is equal to the diameter. Hence, to calculate the height, you simply say the height is equal to the sensor distance plus the diameter, essentially, right? Pretty straightforward. As you know, sensor distance is also in meters. The diameter will also be in meters, right? Now, I would advise you guys, say you were asked to calculate you weren't, say you weren't necessarily given the diameter of the head pulley, you were asked to calculate the diameter of the head pulley, and you use this formula to do so, right? Now, I would advise you to express your diameter, right, when calculating it using this formula, right? Express your diameter in millimeters, right? If if they haven't specified whether you should leave the diameter in meters or millimeters, always leave it or always express it in millimeters, right? That way, when you have to use it in, say, this formula or any other formula where you have to use the diameter, right, you essentially will be working with more numbers, meaning, right, say your diameter is 0, say 72563, right? And then, of course, as you know, you have to round off to three decimal places, right? Always round off to three decimal places. So if you round this off to three decimal places, if you express this in meters, right, this will be 0.726, right? So essentially, you are working with just three numbers, right? For accuracy purposes, hence I'm saying you must express your diameter in millimeters. That way you will work with more numbers, meaning that expressing this in millimeters, you would say this is, say, 725,630, and this will be in millimeters. This way, this is more accurate because you're working with more numbers, essentially. And then when you have to use this diameter to calculate anything like, say, the height, you would then, instead of using 0.726, you would then use, right, instead of using this, you would instead use the 725,630, and then converting this to meters, you would then say times 10 to a negative 3, right? Essentially, though, this is more accurate because you are working with more numbers. Am I making sense here? Right. I'm going to assume I'm making sense. Right. Right. And then you have the formula to calculate the power out. Right. Now, for um, to calculate the output power essentially is the power to overcome, or is the output power is essentially equivalent to um, power to overcome gravity, right? Hence, we use this formula to calculate power, right? So that's the mass flow rate, right? G, already know, is the gravitational acceleration, which is constant. For Meccano, G is 9.81, right? And then, of course, the height, right? So normally we use this. If you can think of, if you remember, you should remember, what is this, conveyor belt, right? The power to overcome friction. This is the formula we use to calculate the power to overcome friction. Not friction, power to overcome gravity, right? So for bucket elevators, the power to overcome gravity is essentially our output power, right? So you'd maybe be asked to calculate the input power or the power from the motor, right? And then in doing so, you would first have to calculate the output power and then the efficiency they would have to give you. And then from the formula of, or from the formula for calculating efficiency, you then work out the power input, right? Now, from the formula for efficiency, making the power input your subject, this is what it becomes, right? And then from this, you get your power input, right, or your motor power, right, depending on how they've asked you to calculate it. They might say input power, or they might say your motor power or power from the motor, right? They will give you an indication though as to which power you need to calculate, right? Of which um, most, if not all the time, it will be the input power, right? So if maybe how they've asked you to calculate the power seems a bit ambiguous, right? One of the indications that you have to calculate power in is if they've given you the efficiency, right? If they've given you the efficiency, that's a clear indication they're looking for, that they are looking for the input power, right? Because you do not necessarily need the efficiency to calculate this here, right? This has its own formula, right? And then the power in doesn't necessarily have a formula of its own, but you can get it from the formula for calculating efficiency, right? Right. And then there is another formula, right? I don't remember if it's in the formula sheet. You would have to check in your formula sheet. For bucket elevators, or the formulas for bucket elevators, or start from formula number 54, right? So check around formula number 54, 55, 56, 7, right? See if you have this formula there, right? I don't quite remember, right? This formula can come in very handy, right? Can come in very handy, right? So if it's not in the formula sheet, just make sure you know this formula, right? Going into the exam, right? Because it can come in very handy, like I say, right? Now, if they've asked you to calculate um, any of these quantities, right? So this here is the volume, right? The volume. So if you have the mass of the material in each bucket, you essentially have the volume of material in each bucket, right? So this formula is for calculating the volume, right? Now to calculate the volume, you simply use this formula here, right? This formula accounts for having to calculate, um, what is this? For having to calculate the span as well as the speed separately, right? So to calculate the volume, right, you simply use this formula, right? This is the mass flow rate. This is the spacing. Rho is the density of each of the material, right? And this refers to the what is this? The chain speed, right, or velocity of the chain, right? This formula can come in very handy, right? Yeah, in fact, I think it is not in the formula sheet, but just make sure, right? Just check if it is in the formula sheet or not. But if not, just make sure you know it's going into the exam because it comes in very handy, right? That you will see as you do more problems based on, or more exercises based on packet elevators. Right? Packet elevators is probably the easiest module in the exam, right? It's a total giveaway. It's very easy, straightforward, right? Um, don't be thrown off by the amount of marks that bucket elevators is in the exam, right? It has absolutely no bearing on how difficult or how easy it is, right? Bucket elevators are very easy, they're very straightforward. If you know the formulas, right, it's simply a matter of applying formulas there. Right? So don't be thrown off by a certain question having a lot of marks, but only requiring, right, small steps to get to what you're looking for. Right? Don't be thrown off by that. That's exactly how it is with bucket elevators. Right? Right? You will get a question, for instance, where you just need to use this formula, right? But the question is say out of 6 marks. So that can throw some people off. You might think that you did something wrong, or maybe you didn't understand the question. That's not the case, right? Bucket elevators just have inflated marks for some reason. I don't know why, but that's how it is, right? It's a giveaway module, but definitely don't go in the exam not understanding how to apply the formulas for bucket elevators, right? Because bucket elevators, hence I'm saying bucket elevators are probably the easiest module, right, in Mechan N5. Are we clear?
Yeah, thank you for that, sir, because I think that would have taken us, a lot of us, by surprise.
Yeah, yeah. It also took me by surprise. Like the first time I did the subject, I couldn't quite understand why it has a lot of marks, and yet the steps to get to what you're looking for are normally very short, right? But that's how it is, right? That's how it is. Very easy, very easy module. So definitely go into the exam knowing this one. In fact, all of them. The only module that might be tricky for you guys is module 5. Module 5 is, what is this? Ropologies. That's the only module that can be tricky for you guys. Otherwise, in test 1 and test 2, you guys did very well. For test 1 and test 2, we did epicyclic reduction and conveyor belts. All right, conveyor belt slash conveyor slash belt drives. Right, they also carry a lot of marks. Right, but you should be fine with that one. You definitely didn't struggle with those chapters, epicyclic reduction as well as module 3 in test 1 or test 2. So you should be fine there. Right. Yeah. The only module that might be tricky for you guys is ropologies. Ropologies, though, we are going to go through over the weekend, say on Saturday. We are going to go through ropologies. I'm going to give you notes for ropologies tomorrow. I can do it today. Yeah, I can do it today. Right. I'm going to give you notes on ropologies today. Right. So you can go over them. And then when you go through ropologies on Saturday, right, you'll have, at least you'll have an idea because you will have gone through the formulas. Are we clear? Right. So that is it for bucket elevators. Right. I believe those are all the formulas that you can expect to use for bucket elevators. Right. So it's a matter of um, being able to tell what exactly you've been asked to calculate. Right. If you're able to understand what exactly you've been asked to calculate, then you'll be fine with bucket elevators. Right. Very easy. Probably the easiest in Meccano N5. Now, I say it's a giveaway because it's around 18, 20 marks. Right? The modules that carry the most marks here are conveyor slash belt drives, bucket elevators, as well as ropologies. Those modules carry around plus minus 20 marks each. So by plus minus, you can expect, say, 18, 17, 18, 20 marks for each of those modules. So three of those modules can essentially give you 60%, can easily give you 60%, or can easily account for 60% in the exam. Right. So module 3, conveyor belts, belt drives, module 4, bucket elevators, and module 5, ropologies. Those carry the most marks in the exam. Right. Now, of those that carry the most marks, right, module 3 and module 4, you should be fine with. The module 3, especially, you did it for test 1 and test 2, right? And then bucket elevators being very easy, you should be fine with that, right? And then ropologies, you can do the entire weekend because at this point, I would think that you are fine with epicyclic gears, reduction, gearboxes, as well as module 3. I would think that you are fine with those modules by now, right? By now it should be a matter of doing some exercises on bucket elevators, one or two exercises on elevators, and then vehicle dynamics is also pretty straightforward, right? So pretty straightforward from the perspective of the formulas we are going to use for vehicle dynamics are not new to you or should not be new to you because we also did dynamics in N3 as well as N4 for engineering science. All right. Any questions before we move on to vehicle dynamics? No questions, right? Okay, let's look at vehicle dynamics. Now, for vehicle dynamics, we do not necessarily have notes for vehicle dynamics, right? I didn't necessarily compile notes, right? Because, like I say, the formulas you're going to use here, you've pretty much dealt with before, with the exception of just one, right? With the exception of just one, and that is the one to calculate the total force applied, which here they refer to as the tractive effort. Right? They refer to it here as the tractive effort. This thing. There's only two. Okay. Yeah, they should be four. You should be fine. Okay. 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 All right. All right. So essentially, for vehicle dynamics, there are two problems that you can expect in the exam. Right. Essentially, what you are looking at is a locomotive. Sometimes you just look at, or sometimes the problem you're looking at is only based on the locomotive alone. And sometimes the locomotive is pulling some trucks, right? Now, for the problem we're looking at currently, you're only looking at a locomotive, right? So they said absolutely nothing about trucks being pulled by the locomotive, right? Now, like any other problem based on dynamics, right? I always suggest that you draw the free body diagram, right, before attempting the problem or before attempting questions based on the problem, right? Always take the information you've been given and draw the what is this the free body diagram. As for dynamics, drawing the free body diagram, right, solves at least half the problem because from this you know where each of the forces are acting, or you can tell the forces that the locomotive or the object is being subjected to, the direction of those forces, right? And then the direction of those forces in conjunction with acceleration, if the locomotive happens to be accelerating, right? And then the direction of the forces in conjunction with acceleration essentially tells you the vector sum of forces, right? So let us look at this problem, for instance. Right, so remember, that's how I prefaced the conversation around vehicle dynamics. I said, essentially, all the formulas we are going to use in vehicle dynamics, you should be familiar with the exception of one. The one for calculating the total force applied. Now, the total force applied, right, is essentially the tractive effort for vehicle dynamics, right? Now let's look at the statement. A locomotive with a mass of 1,000 tons ascends an incline, right? So by ascends, it means it is going up the incline, right? If it was descending, it would mean that it is going down the incline, right? So locomotive with a mass of 100 tons ascends an incline of 0.8% at a constant speed. At a constant speed, the coefficient of friction between the driving wheels of the locomotive and the rails is 0.29, and 80% of the locomotive mass is supported on the driving wheels. The tractive resistance is 80 tons, 18 newtons per ton, right? Now, drawing the free body diagram, right, you essentially have locomotive being this object. The locomotive is 100 tons, right? 100 tons converted to kilograms is essentially 100,000 kilograms, right? And then looking at the forces being subjected, or forces that the locomotive is being subjected to, we know that you have the weight of the locomotive, right? You have the weight of the locomotive. Now, the weight, right, of the object is always acting perpendicular to the ground. So this here being the ground, this being the ground, right? So this being perpendicular to the ground, right, means that we have to essentially resolve the weight into its components. Because remember, for an incline that catches in plane, right, also happens to be at an incline, right? So essentially, this becomes the x-axis and this becomes the y-axis, meaning that if this is perpendicular to the ground, it means that it is making an angle with the catches in plane, right? And forces that are making an angle with the catches in plane, we have to resolve into its components, right? So we have the component parallel to the plane, which is FG parallel. So this is the component of the weight that's parallel to the plane. And then you have the component of the weight that's perpendicular to the plane, which I've named here as FG perpendicular, right? So FG parallel being the one parallel to the plane is mg sine theta, and then the component perpendicular to the plane, which is FG perpendicular, is equal to mg cos theta, right? Now at this point, I would think that you know this stuff, right? The free body diagram, or how to draw a free body diagram of an object that is on an inclined plane, right? So essentially, this is a revision, or I would think that this is a revision for you, right? And then, of course, you have the normal force, right? That offsets the component of the weight that is perpendicular to the plane, right? And then, of course, this is ascending, meaning that there's going to be some total force applied, right, on the locomotive, for the locomotive to go up the incline at constant speed, right? Now we are told here that this is going up the incline with constant speed, right? Going up the incline at constant speed, right? Now, unlike in N3, where if they mention that the object is moving at constant speed, then you assume that it is moving at constant speed throughout, or you are going to assume that it's moving at constant speed for all the questions based on the problem, right? For this, or at this level, right? Sometimes some of the questions can suggest that the can suggest that the object is now accelerating, right? And based on that, you would then have to ignore the constant speed, right? And consider how acceleration affects the calculations, right? Now, let's look at question 5.1, right? Calculate each of the following: tractive effort of the locomotive, right? Now, if you look at the statement, they say that in the rails, they say that coefficient of friction, right, is 0.29, and only 80% of the locomotive mass is supported on the driving wheels. Right. Now, this information, right, the 80% of the locomotive mass is being supported on the driving wheels, that we use only, right, only in calculating the tractive effort, right. Now, in N3 and in N4 for dynamics, right, we never necessarily use a formula to calculate what is this, the total force being applied, right? We never necessarily used a formula for that, right? We'd always get the force being applied from the vector sum of forces, right? Now in N5 and in N6, we also have vehicle dynamics in N6, right? In N5 and N6, we have a formula now to calculate the total force being applied or the tractive effort, right? And the formula to calculate the tractive effort is this one, right? Tractive effort or total force being applied is equal to mu times the mass of the locomotive, right? Times the percentage of the mass of the locomotive that is on the driving wheels times G, right? So obviously this you use if you have been given, if they've mentioned it, right, then you obviously use it. Otherwise, if they haven't said anything, or if they haven't mentioned that only a certain percentage of the locomotive mass is on the driving wheels, right? If they haven't mentioned that, then you simply just use mu m times g, right? But if you're looking at such a case where only a percentage of the locomotive mass is on the driving wheels, then you have to include that percentage, right? So this here is the formula to calculate the tractive effort of the locomotive, right? Or what I've called here the total force applied. Are we clear? Hello?
Yes, sir. Understood.
Right. So this formula, I doubt, is in the formula sheet, but again, you would have to check, right, in your formula sheet, right, if you have this formula. But it should be easy to remember because previously this we used if you had, say, an object on the horizontal plane and you had a force applied, you had F mu, right, you have R, and then you have the weight, right? If the object, now this is entry stuff, right? If the object was moving at constant velocity, right, we would then say Ft, right? All forces going in one direction are equal to forces going in the opposite direction. Because remember, constant velocity means that you have dynamic equilibrium, right? So that dynamic equilibrium means that sum of forces going in one direction is equal to the sum of forces going in the opposite direction. Hence, for that case, Ft would be equal to F mu, right? And then from the formula for mu, remember mu is equal to what is this? This is entry stuff, by the way, right? Mu was equal to F mu divided by R, right? Hence, R can be expressed in terms of mu and R, right? And then R is equal to the weight. The weight is equal to mg, right? Hence, Ft would be equal to mu times R being equal to the weight being equal to mg, right? So I'm saying you should be familiar essentially with this. It doesn't necessarily need to be in the formula sheet, right? Because in N3, right, if you're looking at a problem based on essentially friction, we normally use this, or we normally dealt with such problems in friction, right? Because in friction for N3, the object tends to be moving at constant speed, right? Right. Right. So that is how you calculate the tractive effort of the locomotive, right? And then all you do is substitute that you've been given. The mass is 1,000. Is 100,000 kilograms, right? And then you have a percentage of that mass that is on the driving wheels. Hence, you include that percentage times G for Meccano N5. For Meccano in general is 9,81, right? And this is what you get, right? Now let's look at 5.2, the power delivered or the power
So,
developed. Yes.
sorry, sir. Just a quick question. Say, for argument's sake, I forget or I make a mistake and I put G as 9.8. Would they mark it wrong?
No, not
Uh,
necessarily.
Not that I will. It's just, anything can happen. So I was just curious.
Mm, no, I don't think so.
Okay.
I,
Okay.
I,
Thank you.
I, I don't think so. It's I don't see it as a train smash, right?
Okay.
I honestly,
Because,
unless in the marking guideline it specifies that, because they can do that and say if the student doesn't use 9,81 and uses 9,8 instead, do not give the mark. Unless it says that specifically, right? Then you get a mark for, or you do not get docked for using 9,8 as opposed to 9,81.
okay. Okay. Thank you, sir.
All right. Right. Let's look at 5.2. Power developed by locomotive at a speed of 90 kilometers per hour. Right. Now, again, in N3, we learned that there is a couple of ways we can express power, right? Power in general is the rate at which work is done. So to calculate power, you can use work done over time, right? Now, that work done, remember, if you have forces that are being subjected to, if you have an object and it's subjected to forces, right? Each of these forces has some work done due to it, right? Now, in calculating power in N3, we learned that to calculate power, right, if you're going to use work done, it is going to be the work done, the total work done, so WT divided by T, right? So this stands for total work done, right? And then if you're going to express power in terms of force, then we use total force applied times the average velocity, right? Essentially, average velocity is initial plus final divided by 2, right? So these, for dynamics or for engineering science, this is how essentially we calculate what is this power, right? So looking at this question from this perspective, right? Power developed by locomotive at a speed of 90 kilometers per hour, right? Essentially, we have everything we need, right? We are going to use this one here because we have the total force applied, right? And we can get the average velocity, right? Remember, we are operating under the auspices that this is moving at a constant speed, right? So if an object is moving at constant speed, right, its average velocity will be equal to the constant speed, right? Meaning that if this is moving at constant velocity, right, the initial velocity essentially will be 90 kilometers, and then the final velocity will also be 90, 90 kilometers per hour, right? So if you say this plus this to get the average velocity, If you say 90 plus 90 divided by 2, you essentially going to get 90, right? So to avoid having to do that, just know that if you have an object and it's moving at constant velocity, its average velocity will be equal to the constant speed, right? So essentially, the average velocity here is going to be 90 kilometers per hour, right? So to calculate the power, simply use this formula to calculate power. This you would have calculated here, right? And then the average velocity, like I said, if the object is moving at constant speed, then the average velocity will be equal to the constant speed. So the constant speed being 90 kilometers per hour means the average velocity will be 90 kilometers per hour, right? And then you convert the kilometers per hour to meters per second, hence the divided by 3.6 here, right? And then this is what you get, right? So the product of this gives us 5689.8 kilowatts, right? Now, 5.3, time taken from rest to attain a speed of 90 kilometers per hour up the incline, right? So, like I said, at this level, they have a tendency of switching it up, right? Meaning, in the statement, they will tell you that the object is moving at constant speed, right? And then they ask you a question that suggests that you have to consider acceleration, right? So this question, right, would be such a case, right? They want us to calculate the time it took for the locomotive to move from rest to 90 kilometers per hour up the incline, right? So they want us to calculate time, right? Now, if we look at what you've been given here, you have, we are looking for the time. We know this is moving from rest, so you have the initial velocity, which is 0, and then you have the final velocity, which is 90 kilometers per hour, right? Now you need one more thing here, either the distance, which we do not have, um, as which we do not have, or the acceleration, right? Now we can get acceleration, right? We can get acceleration because all you need to do here is go back to your free body diagram, right? And then say now, this is now accelerating up the incline, right? And then you're going to look at forces going in the same. Now, the way we the way we consider direction for vectors, right? There's two ways in which you can consider direction. One is by using the Cartesian plane, right? By saying forces going up are positive, forces going down are negative, forces going to the right or forces going east are positive, and forces going west are negative. Right, that's one way. And then the other way is by looking at direction from the perspective of acceleration. So the way we do that is forces going in the same direction as acceleration you take as being positive, and forces going against acceleration or the direction thereof you take as being negative. Right. So looking at a free body diagram, right? Forces going the same direction as acceleration is the attractive effort or total force applied, right? Meaning that the total force applied is greater than any and all forces going against acceleration. Forces going against acceleration, you have the total resistance force, right, as well as Fg parallel, right? Now, this tells us that the vector sum of forces, F net, is going to be equal to what? This is in the same direction as acceleration, so you take it as positive. Now, these two are going against acceleration, hence you take them as negative, right? So this gives us the vector sum of forces. So the vector sum of forces, F net, is essentially equal to Ft minus Fr minus Fg parallel, right? Now, what is this? Ft, we've already calculated, right? Fr, we can get because they've given us They said the tractive resistance is 80 newtons per ton, right? So to get essentially FR, you just need to multiply this by the mass of the locomotive in tons, right? The tons are going to cancel each other and you'll only be left with newtons, right? FG parallel, we can also get, right? FG parallel is equal to mg sine theta, right? So we have to calculate this angle theta, right? They say the locomotive with a mass of this ascends an incline of 0.8%, right? Now, the way you get the angle of incline, if you've been given the percentage of the incline, right, is by simply using tan. So the tan of theta is equal to the percentage of incline. So this will be 0.8 divided by 100. And then from this, you calculate theta. All right, so calculating theta from this will be, so this is arctan of 0.8 divided by 100. So this is, so theta essentially is equal to 0.458, right? 0.458, yes. Right, 0.458. All right, so that is how you essentially get 458 degrees. So that is how you would get the angle of incline, essentially, right? So, right. Right, so you get theta, and then once you have theta, then essentially you can get mg sine theta, right? So essentially you can get FR, you can get FG parallel, and then this you've already calculated. So meaning you can get F net. And you know from Newton's second law of motion, F net is equal to MA, right? So from this, you can get F net, right? And then from this, you can get the acceleration, right? Because remember, you have the mass of the locomotive, and then this you will get from um, from this formula for F net, right? And then you can solve for acceleration, right? Right. So that is how you would do it. So essentially here, I have, so instead of first calculating F net, right? Instead of first calculating F net, I simply um, use the formula for this so I can solve for acceleration from this formula, right? So solving for acceleration, I then substituted this, you would have already calculated, right? And then this, remember the rolling resistance or tractive resistance, you were given as 80 newtons per ton, right? And then the mass of the locomotive is 100 tons, right? So to get rid of the tons here and only be left with newtons, you multiply this by the mass in tons. So 80, that is where the 80 times 100 comes from, right? And then you have mg sine theta, right? The mass is 100,000 kilograms. The g is 9.81 sine theta. And then sine theta is, what the hell did I do here? 0, this is wrong. I definitely made a mistake here. So let us fix this quickly. So this is supposed to be 0.8 divided by 100, yes. This is supposed to be sine 0.458, right? Okay, so I guess we'd have to calculate here. Even this is wrong. Okay, so let us calculate this quickly. Can you calculate as well on your side to make sure we get the same thing? 227,592 times 10 to the 3 times 10 to the 3 minus 80 times 100 minus 100 times 10 to the 3 times 9,81 sine 0.458, right? Divided by 100, the mass, it's 100,000, right? So I'm getting here 2,118 meters per second squared. Are you getting the same thing?
Yes, sir.
Right. Right. Then once you have acceleration, right? Once you have acceleration, you can use what is this? An equation of motion, right? So for dynamics, you can always make use of any um, equation of motion formula, right? Now the equation of motion formula that I used here is V is equal to U plus 18, right? And then at this point, you've calculated acceleration, the final and initial velocity you were given, right? Then you solve for t, making t the subject from this formula. This is what you get. So t is equal to v minus u divided by the acceleration, right? And then the final velocity, remember he said calculate the time it took for the locomotive to move from rest to 90 kilometers per hour. Right, so the final velocity is 90 kilometers per hour. Converting this to meters per hour, you divide by 3,6, right? And then the initial velocity is 0 meters per second, right? And then this here is 2,118, right? And then we are going to get 90 over 3,6 minus 0 divided by 2,118. So I am getting here 11,804 seconds, right? Now I would suggest that for seconds, you do not use S, right? Always use SEC for seconds, right? Because you don't want your marker to confuse S for a 5. Are we clear? Hello?
Yes, sir.
All right, so that is what we get. Right. Any questions so far? No questions.
No, sir.
Okay. Now let's look at 5.4. 5.4 is calculate the distance the locomotive would travel during the time calculated in question 5.3. Right. Now this one is very simple. Remember, I said you can use any equation of motion or kinematic equation, right? Depending on what you're looking for and what you've been given or what you have. Right. So now they want the distance. Right. The simplest way to calculate the distance. Right. The simplest way to calculate the distance is by using this equation of motion. Right. This one here. Maybe some of you will remember it as S is equal to the average velocity times time. Right. Average velocity is equal to the final plus initial velocity divided by 2 that you multiply by the time, right? And then, of course, this you will have calculated here. The initial and final velocity you've already been given, right? And then you'll be able to get your distance, right? Now we have to fix this. So this is 11,804. 804, right? So we say this divided by 2 times the 11,804. So I'm getting 147. I'm
Yes,
getting
sir.
147,55 meters, right? And that is how you would calculate the distance traveled. Right, so vehicle dynamics is also very easy, very, very easy, right? Now, vehicle dynamics is easy because you are able to tap into what is this? Um, 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 I want to say previous knowledge, but yeah, previous knowledge, the knowledge you got when doing engineering science N3 and N4, because we essentially applied the very same principles we applied even then, right? With only the exception of the formula to calculate the tractive effort, or what I call there as the total force applied, right? That is how you would attempt questions based on vehicle dynamics. If they only considered the locomotive or the mass of the locomotive. Right? Remember, I did say that you get problems where they only consider the locomotive, and then sometimes they consider the locomotive as well as the trucks it is pulling. Right? Now, here's a challenge for you. You are going to go through, I will send this in the group, right? You are going to go through this problem, right? This one here. Now, this problem is based on a locomotive, right, hauling trucks or pulling trucks, right? I want you to see if you can figure it out on your own, right? Essentially, you do the same thing, but now the only difference is that instead of just considering the locomotive, you're considering both the locomotive as well as the trucks it is hauling or the trucks that it is pulling, right? The formula to calculate the tractive effort of the locomotive, right? If you see here, this specifies the tractive effort of the locomotive. So you are still going to use this formula, right? So the mass will always be the mass, or to calculate the tractive effort or total force applied, the mass will always be of the mass of the locomotive only, right? So the major difference will be in calculating FG parallel, right? Because remember, you're not only considering the mass of the locomotive, but the mass of the locomotive as well as the mass of the trucks it is hauling. That is why here, instead of having both masses, right, I simply added the mass of the locomotive, which is 100 tons, as well as the mass of the trucks being hauled, which is 500 tons. So adding that gives you 600 tons. 600 tons converted to kilograms is 600,000 kilograms, right? So I want you to look at this one on your own, right? First, attempt it, right? Look at the question, attempt it on your own, right? And then look at the solution. I will post it with the solution, right? But I want you guys to test yourselves as to whether or not you understood what we did here today by doing this one. Are we clear?
Yes, sir. Okay, sir. Just a quick question. So what you are saying is by 5.1, they ask to calculate the tractive effort of the locomotive. Do you then, even if they specify the locomotive, do you then use the total value or the total mass?
No, you will always use the mass of the locomotive.
Okay.
Right? To calculate the tractive effort, you only use the mass of the locomotive.
Okay, so it's just for the rest you would use the total mass.
Yes, exactly.
Okay. Okay.
So what this should tell you is that the formula to calculate the tractive effort is only this one, where the mass will always be the mass of the locomotive. Right? So this is regardless of whether or not the locomotive is hauling trucks or it is not hauling trucks. Right? It's regardless of that. Right? Meaning the formula to calculate the tractive effort is only this one. Right? It is not dependent on anything. Are we clear there?
Yes.
Right. And then for everything else, you would then have to use the total mass. If you see here, I use MT for total mass. I actually should have done the same thing here as well. Now, it's unlikely that you'll have to use this, but I'm going to include it anyway. So total mass times G cos theta. Right. And then also just a hint here on how to calculate the total resistance. Right. Now, when the locomotive, or if it's been mentioned that the locomotive is hauling trucks, normally they give you the tractive resistance, right, or rolling resistance of both the locomotive and the truck, right? So meaning that since you have the rolling resistance of the locomotive as well as the rolling resistance of the truck, right, to get FR, right, or total FR, it will then say the rolling resistance of the locomotive multiplied by what? The mass of the locomotive plus the rolling resistance of the trucks, maybe let me say TR for trucks, times the mass of the trucks. Right? This is essentially the only time where you wouldn't use the total mass because the rolling resistance for the locomotive is different from the rolling resistance of the trucks. Are we clear? Hello.
Yes.
All right. Then if there are no more questions, we are done here. Right. I'll still be available and to answer questions. If you have questions and I haven't slept yet, then I'll answer your questions on WhatsApp.
Okay, thank you. So are you gonna post this video in a group or are you gonna put it on the channel?
I'm gonna put it on the channel. In the group, I won't be able to. It's probably too big. Right? It's probably too big. But uh, I don't know if I'm going to be able to do it tonight because the thing is, one of the reasons why I haven't been available is because I lost both of my devices that I was using. Right, this is a new device, iPad. Right, so I currently do not have a laptop. Right, so I'll only have access to a computer tomorrow at work. I am going to try to upload this on YouTube using the iPad, failing which I'll only be able to post tomorrow morning at work.
Okay, so if possible, if it's not too much effort, if it's not too much, yeah, can you maybe just take a screenshot and just post the screenshots in the group
What
of
screenshot?
the, like take a screenshot of the calculations and then post it in the group.
Screenshots of the calculations.
Yeah, like you did here now. Obviously, just to as a reference.
I'll send the calculations in the group.
Oh, okay, okay, thank you.
Yeah, yeah. Right. So, like I said, if I'm able to post this using my iPad, then I will do it. Failing which, I'll then post it only tomorrow at work. Ne?
Okay, thank you, sir.
All
Thank you,
right.
sir.
Any more questions?
No, sir.
Right. So I'll send you the calculations we did today, and then I'll also send you notes on what is this? Okay, notes on ropologies. I'll send you tomorrow, not today. It's fine. Today, focus on what we've covered so far. So, bucket elevators, vehicle dynamics, as well as what's the other one? Elevators. So, elevators will go through tomorrow.
Okay, so if you when you're referring to vehicle dynamics and the book I have, is that the same thing as rail and road traction?
Yes.
Okay.
Yes.
Okay, great.
All right. Any more questions? All right then. We are done here.
All right, thank you, sir. Enjoy your evening.
Yeah, you too, man. Thanks.